Hi all, my name is Vital Patel. Today I'm going to present the paper Google File System. So it was first introduced by the authors Sanjay Khemawat, Howard Kopioff and Shen Tang in the year 2003. The authors were part of the Google's System Infrastructure Group. So first of all, let's start by understanding what is a file system. So, a file system is a method for organizing and storing computer files and their data. As a companies like Google handles a massive amount of data, and there is a need for a distributed file system that can scale efficiently. The Google file system is a distributed file system. So, what is a distributed file system? So, in a simple word, it is a file system that is not present on a single machine. Instead, it is distributed across the set of machines. The way it is done is you would not realize that a file distributed across the multiple machines or you is just like a create a file, read a file, update a file, delete a file. But behind the scenes, system is taking care of distributing it. It is highly scalable and fault tolerant system that can store and manage petabytes of data. Google file system is designed to handle large files, typically in the range of hundreds of megabytes to multiple gigabytes. It is optimized for sequential reading and writing rather than the random access, making it ideal for storing large files like web pages and log files and many more. Now, here, key point is that it is in the key sense that it is running on the top of commodity hardware. Now, what is commodity hardware? Which means that they are not expecting that this cluster can run only on specialized hardware. Any machine, let's say, which is available in the market, you can plug it in the cluster and it would be a part of the system. So there is no specialized hardware requirements, which make this system a little bit more special. So the motivation behind developing GFS was to address limitation of the traditional file system in managing petabyte of data across the distributed environments. So let's discuss the problem faced by the Google. Excuse me. Firstly, let's talk about scalability. Imagine Google handles petabyte of data and billions of files. Now, traditional file systems weren't built to handle such large amount of data. So, when Google tried to expand and store more data, the old systems couldn't keep up. This scalability issue was a major roadblock for Google's growth and innovation. Another significant challenge Google encountered was reliability. They require high availability and data durability. Unfortunately, traditional file systems were prone to failures, and recovering from them was not only a time consuming but also a risky for Google's operation. Next up, performance. So, performance was the concern. Google's application demanded fast access to data. However, traditional file systems weren't optimized for large scale data processing and storage, resulting in slower performance than what Google's required to meet their user demands. And last is cost. So it was a critical factor. Google needs a cost effective solution for storing and managing their large amount of data. Traditional file systems were expensive and couldn't scale economically to meet Google's needs without breaking the bank. Now let's go a little bit deeper into it. First of all, if you think about it, the normal file operations you are doing with all files will be a typically huge multi-GB files. Now you have two options over here. Either you store these entire multi-GB files on a one machine as a single piece, otherwise you break it into chunk and distribute it, right? It does not mean that you don't have a single final machine, but these are two typically ways to approach that storing entire file together or break it into chunks. So let's start by storing entire file together. So what if we do that? What if we store entire file together? It is harder for your system to find out contiguous disk space. It is very difficult to write. And another way is divide files into chunk. We will see in the details. In the image, you can see that C1, C2, C3, C4 and C5 were divided into chunks. So here the architecture of the GFS. In the given image, it shows the relationship between master node, GFS chunk server, and GFS client. Each component plays an important role in the storage and retrieving the data within the system. So, the master node is responsible for coordinating access to the file system, managing metadata, and controlling data placement. Chunk server stores actual data chunks and handle read and write requests from the client. Client interact with both master and chunk server to access and manipulate data. We will talk in detail about chunk server and master node. So here, whenever client want to read the file, it will ask for the file name, and if it is in middle of the reading a file, it can ask for chunk index. So let's say I want to read fifth chunk of the file system. So I want to read fifth chunk of the file. In that case, GFS master from its table give ID of the chunks, and all the chunks have our IP address where the chunk has replica. Once client has all those IP address, it can then using a particular chunk handle, which is that ID. It can directly go to the chunk server and read that data directly from the chunk server. So it is important to note that GFS client doesn't read the data from GFS master. It only reads a metadata about the file. So actual reading done between the GFS client and GFS chunk server. Let's talk about the chunk server. File is chunked and stored across the cluster. The machine where these chunks are stored are called chunk server. So here job of the chunk server is to store the chunks. Each chunk is identified the unique 64-bit chunk handle, which is used by the master server to locate and access the chunks. It handles the read and write request from the clients. Here we need a complete fault tolerance. So what if one of the chunk server got down and become inaccessible? So how do we solve this? So GFS proposes a replication factor, which means one chunk has copies of two or three. In the image, you can see the red chunk is divided into uh, the chunk server 1 and chunk server 2. The blue chunk is replicated into 1 and 3, and yellow chunk is replicated into chunk server 2 and chunk server 3. So if any of the chunk server got down, we can still access other chunk. So here are some benefits of breaking files into chunks. One is parallelism. So chunking enables parallel processing, improving system performance by allowing multiple read-write operations simultaneously. Second is load balancing. So distributing data across multiple chunk server helps in load balancing within the file system by evenly distributing chunks among the server. GFS ensures optimal resource utilization. The next is easy migration. So in the event of chunk server failure or overload, GFS can seamlessly migrate chunks to other available servers without disrupting ongoing operations. Then there is a easy storage allocation. The system dynamically allocates chunk to the chunk server based on the available resources and workload demands. And last is reduce network overhead. So by storing and accessing data into chunks, GFS minimize network overhead. This is achieved by transferring only the required chunks over the network rather than the entire files, thus optimizing bandwidth usage. Now, how to decide which chunk is lies on which chunk server? So there is one who knows. So here it comes a role of master node. Master node is very similar to chunk server, but instead of storing the chunk, it holds the metadata. The master node maintains the metadata of the file system, so it's storing name, file size, access control list, chunk server, and which chunk is present on which chunk server. Each serves as a central coordinator in the GFS. So master node has a responsibility to keep track of all the chunks and their location along with the file size, client operation, and everything. The master node also performs load balancing by assigning mappers to the chunk server based on their current workload. This ensures that the workload is evenly distributed among the chunk servers, preventing any single server from becoming overload. Uh, Here, master node also need to monitor the health. It uses health periodic heartbeats. So if chunk server is down, master node balance the chunks and copies them to the other service. Mm, Now let's see how write operation is worked. If a client wants to write a file, it will ask to a master to create a file and master will give location of all the chunk server which are free right now. Now, which means that if there are few chunk server which are only 10% or 20% full, it will give a more priority to those chunk server and give the client three such as possible chunk server which are free where the client can write the data. Out of those three server, client will find the closest server and pass all the data to it. So in this case, given in the figure, the replica A was the closest and client sent all the data to replica A. And this chunk server in turn will pass on the data to a next replica, which is primary replica, and so on. So client's responsibility is only to pass the data with the to a single replica. That is how bandwidth of the system correctly utilized. Here, here are some of the key features of the system. First one is chunking. So the GFS divides files into fixed size of chunks of 64 MB. This chunking approach allows for better data management and distribution. It also enables the system to handle large files efficiently by storing them across the multiple chunks. These chunks are then distributed across the multiple chunk server. By allowing efficient data management, GFS uses a chunk server architecture where each server is responsible for storing and retrieving chunks of data. Additionally, chunking also allows parallel read and write by improving overall performance of the system. Next is a single master. In the system, there is only one master server for an entire cluster. So even if there are hundreds of clients accessing the files, writing the files, or reading the files, or creating the files, and there are hundreds or few thousand servers, all these operations can still be done using only a single master. And that is because each chunk is of a relatively large size, which is 64 MB. So for each file, the metadata, which is unique 64-bit ID that needs to be stored for each chunk, multiplied by 3 replicas, is a very small amount of data that master needs to store. It minimizes the client interaction for a better performance. Next is atomic record append. One of the key requirements for a system that uses by Google was ability to efficiently append the data to the files. GFS introduced the concept of atomic record append, which allows for an efficient appending of the data to files. In this approach, a file is divided into fixed size of the chunk. Each chunk is treated as an independent entity. These allow for a multiple client concurrently append to the data same file without any conflicts. The next is replication. Each chunk of data is replicated across the multiple servers to ensure that high availability and reliability. This replication factor can be adjusted based on the application's requirement. The next is snapshotting. The GFS supports snapshotting, which is the ability to take point-in-time snapshot of the file system. This feature allows for a data backup and recovery in the case of data corruption or accidental deletion. This is also called a copy on write. Snapshots are also useful for data analysis and testing purpose. Fault tolerance refer to the system's ability to continue operating even in the presence of failures or fault. Now let's see one of the primary challenges encountered during the development of GFS. The Google file system operates across the thousands of servers, making it susceptible to a recurrent component failures. These failures can range from a hardware malfunctions to a network issues, posing a significant threat to a system's reliability and data integrity. To address the challenges of recurrent component failures, the Google file system employs the strategies of high availability, data integrity, and the diagnostics tools. So, high availability involves designing the system to withstand failures gracefully by replicating data across the multiple nodes and ensuring the redundancy in the critical component. In addition, high availability, maintaining the data integrity is a paramount in a distributed file system. By implementing the mechanisms such as checksums and redundancy checks, the GFS safeguards against the data corruption and the loss. Even in the face of component failures, GFS provide comprehensive tools for monitoring and diagnosing system issues. Logging mechanisms capture systems events and errors for analysis. Performance monitoring tools assist in identifying and resolving the bottlenecks. This is the micro benchmark conducted on the GFS system, giving the performance and scalability in handling diverse operations under different workloads and network conditions. The tests were carried out on a GFS cluster comprising one master, two master replicas, 16 chunk servers, and 16 clients. During the read benchmark, clients were tested with reading 4 MB regions from a 32 GB file set. This is repeated for 256 times. For a write, clients were instructed to write 1 GB of data to a distinct files in 1 MB of chunks. In the record append benchmark, multiple clients appended the data simultaneously to a file. Now let's see real world cluster. Now looking at the table 2, we see a snapshot of two GFS cluster, cluster A and cluster B, that is used by the Google. Cluster A boasts 342 chunk server and 72 TB of available disk space, while cluster B has 227 chunk server and 180 TB available. What is interesting is cluster B's efficiency with the 155 TB used of disk space despite the fewer chunk server. These numbers gives us a peek into a scale capacity of the real world GFS cluster. Now turning into table 3, we observe read and write rates between cluster A and cluster B. Cluster A shows marked performance for a read operation, suggesting a focus on the data retrieval task. On the other hand, cluster B demonstrates more balanced workload between read and writes. Both cluster effectively manages their workload, ensuring the smooth operation without overwhelming the master node. These findings highlight the efficiency and the scalability of the GFS cluster in a practical environment, providing the valuable insights into their operational dynamics. Now let's see in the section detailed breakdown of the workload of GFS cluster. So there are two clusters, X and Y. Cluster X is maintaining for a research and development, and while cluster Y handles production data processing. Looking at the table 4, it shows the size of reads and write records append, which help us to understand how data is being used in each cluster. For example, small read under 64 KB are often from tasks that are search for small bits of data in large files, while large reads over a 512 KB are usually long sequential read throughout the entire files. Similarly, write size also vary, with larger write often resulting from a writers storing a lot of data at once. Now turning into table 6, we see a breakdown request made to the master node in each cluster. It tells us what kinds of operations are being performed, like finding the location of data chunks or demonstrating who has permission to edit a file. We notice the difference between the clusters, such as cluster Y is handling more delete requests due to its role in managing frequently changing the production of data. So, in the conclusion, Google File System has a game changer in the storage industry through the combination of innovative techniques such as master slave architecture, chunking, replication, and simplified APIs. GFS achieves high reliability, scalability, and performance, crucial for supporting Google's vast array of services. Its architecture has also influenced the design of other distributed file systems, and its impact can be seen in many modern storage solutions. With the ever increasing demand of data storage, GFS will continue to play a significant role in the storage industry. Thank you.